The basic equation in quantum theory is the Schrödinger equation. It is an equation that cannot be derived, but it has proven to be correct in practically all applications. For one particle in one dimension, it is I h bar ddt of uppercase psi of x and t equals to minus h bar squared over 2m, where m is the mass of the particle, times d squared dx squared of psi of x and t plus v of x times psi of x and t. The solution of this equation gives a wave function. The wave function psi in turn allows us to compute all probability distributions for all measurable quantities. The left-hand side contains the time derivative of the wave function. Therefore, this equation is called the time-dependent Schrödinger equation. The right-hand side contains two terms. The first term represents the kinetic energy, T, and we can write it with an operator, T hat operating on psi of x and t. We can write the kinetic energy operator in terms of the momentum operator, T equals p squared over 2m. In one dimensions, the momentum operator equals to h bar over I ddx. The second term represents the potential energy, and we can write it with an operator form V operating on psi of x and t. V is a simple multiplication operator. The total energy is the sum of the kinetic and the potential energy. It is written in operator form as h hat operating on psi of x and t, where h is called the Hamiltonian operator, or simply Hamiltonian. The Hamiltonian is the operator for the total energy of a system. We cannot solve the Schrödinger equation without knowing the potential energy function V of x. However, we can look at a special case of wave functions. Some wave functions can be written as a simple product of a position-dependent part and a time-dependent part. Psi of x and t equals lowercase psi of x, this is the position-dependent part, times f of t, this is the time dependence. For these type of wave functions, the Schrödinger equation can be separated into two different equations, one for phi x and one for f of t. The position equation becomes h hat operating on lowercase phi of x equals e, a constant, times phi of x. This is an eigenvalue equation for the Hamiltonian, the total energy operator. E is a constant, is the eigenvalue, and represents the energy eigenvalues associated with the energy eigenfunctions lowercase phi of x. This equation is very important. It is referred to as the time-independent Schrödinger equation. In contrast, the initial equation, the Schrödinger equation, which can be written in a simple, more compact form as I h bar ddt of psi of x and t equals h hat of psi of x and t, is called the time-dependent Schrödinger equation. Back to the special case. The position equation is a time-independent Schrödinger equation. The time equation is very simple and can be solved straight away. The solution is f of t equals to e to the negative I e t over h bar, where e is the energy eigenvalue from the position equation. Putting the results together, we get for a simple separable wave function psi x of t a product of lowercase psi of x times e to the negative I e t over h bar. Uppercase psi of x is the full wave function. Often, people refer to lowercase x as the full wave function, even though it's not the full wave function, it's only the position part.